Next, we want to look at some examples of how we can find the intervals on which a function is concave up or concave down, looking at the sign of the second derivative, as well as identifying the inflection points. So we're going to be doing things that are really similar to what we were doing in the previous section when we were analyzing the sign of the first derivative to talk about increasing and decreasing intervals. We're going to calculate the second derivative, we're going to set it equal to 0 or find where it's undefined, and then we're going to set up a number line, pick test points, and determine the sign of the second derivative on each of those intervals, and that will allow us to conclude what intervals the function is concave up and concave down. So I'm going to look at 4 of the functions that we looked at in the previous section, and we're going to start. I've already calculated the first derivatives for us to remind us of where those were, so we'll start off by just calculating the second derivative and going from there. So our first example is a polynomial that we looked at last time, y equals 6x cubed plus 18x squared. Our second derivative is going to be 36x plus 36. And so if I want to solve y double prime equal to 0, I set the second derivative equal to 0. I get 36x equals negative 36 divided by 36. I get x equal negative 1 as my only value. And so I set up my number line. And I'm going to pick test points. I'll choose negative 2 and 0. And then we'll look at the sign of y double prime. So y double prime of negative 2 is going to be negative 72 plus 36. That's definitely less than 0. And then y double prime of 0 is going to be 0 plus 36. That's definitely positive. So then we look at the behavior of y. If the second derivative is negative, that means that it's concave down. If the second derivative is positive for numbers bigger than negative 1, that means that it's concave up. And I've got a switching concavity here, so this is an inflection point. And so we summarize, y is concave up on negative 1 to infinity. Y is concave down for numbers less than negative 1. And y of negative 1, which is going to be equal to negative 6 plus 18, it's 12. So negative 1, 12 is an inflection point. So we've got an inflection point. We've got our intervals of concave up and concave down. Now let's do that for another function that we looked at last time. Y equals 2x times e to the negative 1/4 x. And I've done all the work in calculating the first derivative, but we were going to start here and apply the product rule to this to find the second derivative. And we'll have to do a little bit of work here. So I've got the product rule in play, and so I'll treat 2e to the minus 1/4 x as my first term. And so y double prime is going to be 2 times negative 1/4 e to the negative 1/4 x times 1 minus 1/4 x plus 2e to the negative 1/4 x times the derivative of 1 minus 1/4 x, which is just negative 1/4. Now I'm going to need to do a little factoring here, so let's pay attention. I've got 2 times negative 1/4 times e to the negative 1/4 x here, and I've got that same product right here. So that's a common factor. So I'm going to pull that out. So 2 times negative 1/4 e to the negative 1/4 x, and what's left behind is 1 minus 1/4 x, and I've pulled everything out of this, and so that gives me a plus 1 there. And so I'm going to get negative 1/2 e to the negative 1/4 x times 2 minus 1/4 x. So if I want to set y double prime equal to 0, this is never 0. And so I'm looking at 2 minus 1/4 x equal to 0. 2 equals 1/4 x. or x equals 8. So again, I just have one place to look at here to determine concave up and concave down behavior. So here's my number line. I'll choose some test points. I'm going to choose 0, because if I can choose 0, I like to, and I'll choose 10 here. And so I want y double prime of 0. That's going to be, and I'm going to use this formulation right here for calculating my values of y double prime. So I get negative 1/2 e to the 0 times 2. That's a negative quantity. I've got a negative times a positive. Y double prime of 10, on the other hand, is going to be negative 1/2 e to the negative 10 over 4 times 2 minus 10 fourths. 10 fourths is 2.5. So this is negative, and so that's going to make this a positive quantity. So this is the sign of y double prime, and then I get the behavior of y. So looks like I was concave down here because the second derivative was negative. I'm concave up here because the second derivative is positive, and so I can summarize y is concave up for numbers bigger than 8. It's concave down for numbers less than 8. And I have an inflection point at x equals 8. And so y of 8 is going to be 2 times 8 times e to the negative 8 over 4. That's 16e to the negative 2. So my inflection point is 8, 16e to the negative 2.